In this lesson, we will be looking at Pascal's triangle and the binomial theorem. So starting with Pascal's triangle, Pascal's triangle tells us several pieces of information, and it actually helps us apply the binomial theorem. So in the triangle, what you'll see is that there are specific row numbers starting with row 0, and the first value that you see in row 0 is just number 1. In row 1, you have numbers that are stated as 1 and 1. In row 2, we have 1, 2, 1. Row 3, we have 1, 3, 3, 1, and that pattern sort of continues. There is a pattern between the numbers, and we'll talk about what those patterns are. One of the things I want you to notice is that in Pascal's triangle, you'll notice that there is one more term in each of the following rows than there was in the row previous to it. So in the first row, there's only one term. In the second row, there's in row 0, there's one term. In row 1, there's 2 terms. In row 2, there are 3 terms. In row 3, 4 terms, etc., etc., etc. So there are many patterns in Pascal's triangle. Each row of the triangle begins and ends with a 1, as you can see. Each term is the sum of the 2 numbers above it. So what this means is, if I look at a specific term in the triangle, the way this number is determined is by adding the numbers that are above it. So if I add 1 plus 2, I get the value 3. Okay, same with, let's say we go down here to this 5. If I add 4 plus 1, I get the value 5. So each of the values in Pascal's triangle are created by adding the numbers that are directly above it. The sum of any row can be represented as 2 to the exponent the row number. So what this means is, if I wanted to know what all the terms in row 3 of Pascal's triangle add up to, all I would need to do is, so if I wanted to look at row 3, all I would need to evaluate is 2 to the exponent 3, and that'll give me a value of 8. And if you actually look at row 3 here, and I add 1 plus 3 plus 3 plus 1, I get a value of 8. So what this actually tells you is some important information. And if you look at the fourth pattern that's represented in Pascal's triangle, you'll notice that it says each number in Pascal's triangle describes a number of paths. So what this tells me, so each of these numbers, what it tells me is the number of different ways that I can get to that particular spot in Pascal's triangle. So for example, there's only one way to get to this value here. And that way is to start at the top and continue towards the left and get to that 1 there. What the 3 here tells me is that there's 3 different ways to get to that particular point in the triangle. Here's the first way, so moving along the left and then coming down to the 3. The second way is to move down 1, across to the 2, and then back down to the 3. And the last way is to go to the right 1 and then go diagonally across to the 3 again. So that 3 tells me that there's 3 different paths to get to that particular number. So when you're looking at the sum of the of any row, you'll notice that what that represents is the total number of paths to get to any of those values in that particular row. So if I wanted to know how many paths there were to get to any of the values in row 3, all I would need to do is either add the values here or look at 2 to the exponent, that number, to figure out the answer. Okay. Now, aside from just the patterns between the numbers, there is a significant use for Pascal's triangle, and the use for Pascal's triangle comes from looking at the binomial theorem. So why do we care about Pascal's triangle? Because it can be applied to binomial theorem. So let's take a look at what binomial theorem means. So the binomial theorem is a simple way to express a plus or minus b to the exponent n in expanded form by using Pascal's triangle. So whenever you have a binomial raised to some exponent, you can use Pascal's triangle to actually help you expand it without having to do several different expansions. So for example, if you had x plus y to the exponent 7, instead of writing this out 7 times and multiplying each pair at a time to try to figure out what the expanded form of this would look like, the binomial theorem shows you a faster way of writing x plus y to the exponent 7 in expanded form. So the way you do that is by first looking at the row number in Pascal's triangle based on what the exponent is on the binomial. So the row number in Pascal's triangle represents the exponent n of the binomial. So for example, if I was looking at an exponent of 7, that means that I would be corresponding this to row 7 in Pascal's triangle. Each number in that row of Pascal's triangle represents the coefficients of each term when expanded. So for example, each of the terms in the 7th row of Pascal's triangle would represent the coefficient of each term when I expand the binomial. And then what you'll notice is the exponents of the first term decrease by 1 and the exponents of the second term increase by 1 each time. And right now I know this might seem confusing, but we are going to look at some examples. So we're going to start by looking at an example of binomial theorem, and then we'll look at an example of Pascal's triangle. So our first example looks at the binomial theorem. So for instance, if we have 2x minus y to the exponent 3, what this means is because we have an exponent of 3, this tells me to look at row 3 of Pascal's triangle. And if you look at the 3rd row of Pascal's triangle, remember how to label your rows. So that's row 0, row 1, row 2, row 3. In row 3 of Pascal's triangles, I have the terms 1, 3, 3, and 1. And what these represent are the coefficients of each of the terms in the expanded form of this binomial power. Okay? And so one way to do this is to actually write 2x minus y times 2x minus y times 2x minus y. But the problem is if you have an exponent like 7, this process can be really, really tedious. Okay? So instead of writing it this way, we're going to find a different way of expanding that binomial. So the way we're going to do this is we're going to look at the 3rd row of Pascal's triangle. And what this will represent is are the coefficients of each of the terms in Pascal's triangle. Now, after each coefficient, you will be looking at the first term and the second term of the binomial. So I'm going to write 1 and then include 2 brackets, plus 3 is my next coefficient. I'm going to include the 2 brackets, plus 3 is my next coefficient. I'm going to add my next 2 brackets, and then plus 1 is my last coefficient. I'm going to include my brackets as well. Now, inside these brackets, what I'll end up getting is the first term goes inside each of the first brackets, and the second term goes in the second brackets. And the second term is negative, so I need to make sure I include the negative y. Okay, now what happens here is, because you're looking at a degree 3 polynomial, because the exponent here is 3, what that means is the sum of the exponents on each of my terms should only be 3. So the way you apply the binomial theorem is the highest exponent goes on the first term, so the highest exponent is 3, and this exponent continues to decrease as you go across the different terms. Similarly, when you're looking at the second term, you're going to have to start with the lowest exponent possible, which is 0, and this exponent is going to increase to the highest exponent possible, which is 3. Okay, so the first term gets the highest exponent and decreases from there. The second term gets the lowest exponent and increases from there. From here, you're just applying each power. So this is 1 times 8x cubed times 1. So 2x cubed is equal to 8x cubed. Negative y to exponent 0 is 1. Plus 3 times 4x squared times negative y. Plus 3 times 2x times negative y to the exponent 2 is positive y squared. Plus 2x to the exponent 0 is equal to 1. And negative y to exponent 3 is negative y cubed. And then from here, all you need to do is multiply each of the factors in each term. So this will give me 8x cubed. 3 times 4 times negative 1 is minus 12. X squared y. Positive 6. Xy squared. And then minus 1, or just minus y cubed. Okay, so there's the binomial expanded using the binomial theorem instead of applying the distributive property over and over again. Okay, so this is how you would apply the binomial theorem. And the answer is there as well, so we can just check our work. Positive 8x cubed minus 12x squared y plus 6xy squared and then minus y cubed. Okay. Okay, in terms of a Pascal's triangle example, here I have an example with the CN Tower. And it says, Jimmy wants to get to the bottom of the CN Tower. Due to a blazing fire, the elevators have stopped, and Jimmy needs to use an alternate route to get down. Determine the number of routes Jimmy can take to get to the ground. Think of C as the top of the building and R as the ground. Hurry up before Jimmy runs out of time. Okay, so in this problem, what you'll notice is there's a similar pattern, much like Pascal's triangle happening here. So this is the first term, then this 2 terms here, and then 3 terms, 4 terms, 5 terms, 6 terms, 7 terms, you'll notice that each row increases by 1 extra term, and that's the same pattern that you see when you look at Pascal's triangle. Now, because it wants to know the different number of roots to get to the ground, what we're trying to figure out is how many different roots there are to get to any of these terms at the bottom of Pascal's triangle. Now, one of the patterns that we talked about earlier when we were looking at Pascal's triangle is that to figure out how many different ways to get to the bottom here, we can find the sum of the rows, sum of the terms in this row, or the other way to do it is to use a shortcut, which is to look at 2 to the exponent of the row number in Pascal's triangle that we're looking at. So this would be row 0 where the C is, row 1 is where the N is, row 2 is where the T is, row 3 is where the O is, row 4 is where the W is, row 5 is where the E's are, and then row 6 is where the R's are. So because we're looking at row 6 of Pascal's triangle, we can look at 2 to the exponent 6 to figure out the different number of roots to get to the bottom of the CN tower. So in this case, that would be 64. Okay, so there should be 64 different ways that Jimmy can go from the very, very top of the CN tower down to the very bottom. And you can try to sit there and actually count them. So this would be one way. This would be a second way, and a third way, and a fourth way, and a fifth way, and like you can keep doing this, or you could just use 2 to the exponent row number to figure out the different ways. Another way to do this also is to actually determine what the terms are in this row of Pascal's triangle, and then to find the sum of them, since each term tells you how many different ways there are to get to that particular point in the triangle. So what I can do is fill in Pascal's triangle. So I would say 1 is at the top, then start and end at 1. This would be 1, and then this is where it gets interesting because now I have to add the numbers above it to get to the number below. So 1 plus 1 is 2, ends with a 1 again. It's the beginning of a new row, so that's 1. 1 plus 2 is 3, 2 plus 1 is 3, and then 1. There's only one number above this, so I know this is going to be a 1. 4, 3 plus 3 is 6, 4, 1. No, there's only one number above it, so I know this is going to be a 1. That's 5, 10, 10, 5, and 1. There's only one number above, so I know that's 1, 6, 15, 20, 15, 6, and then 1. Okay, so 10 plus 5 is 15, 10 plus 10 is 20, etc. And so if I add each of these terms together, so if I do 1 plus 6 plus 15 plus 20 plus 15 plus 6 plus 1, what I do end up getting is 64. So what that tells me is that there are 64 different ways that Jimmy can take. So therefore, there are 64 routes Jimmy can take.